Bismillahirrahmanirrahim. Assalamu alaikum dear students. I'm Arif and I welcome you all to the next session of System Programming with Linux. Today we are going to do a scuba diving as to how the Linux CPU scheduler actually works. We'll start with a quick recap of some important scheduling related terms and a brief discussion on some standard CPU scheduling algorithms. We will see how the Unix System V Release 3 process scheduler works. We will see the data structures involved and the working of Linux famous constant time scheduler. And then finally the Linux CFS scheduler, completely fair share scheduler. Before closing, we will introspect various scheduling related parameters using the famous Linux Schedtool, and finally see some related system calls that can be used to query and set the scheduling parameters from within a C program. So let's start playing. Well, we all know that scheduling is a matter of managing queues to minimize queuing delay and to optimize performance in a queuing environment. And process or CPU scheduler is in a multitasking OS is actually a kernel component that decides which process runs when and for how long. We all know that multitasking OS comes in two flavors, the preemptive multitasking OSs and the cooperative. And some examples of cooperative multitasking operating systems are Mac operating system 9 and earlier versions, Windows 3.1 and earlier. Well, dear students, before we proceed, let's differentiate between the preemptive and the non-preemptive kernels. Well, at any instant of time, a system can either be executing in user mode, that is executing line of code written by the programmer, or kernel mode, that is executing line of code written by the kernel developer. And this can happen in a process context, that is a system call is made by the programmer, or in interrupt context. So keeping this in mind, let me define three different types of operating system kernels: preemptive, reentrant, and non-preemptive. A preemptive kernel is one that can be preempted both in A and B, that is in process context as well as in interrupt context, while the reentrant kernel can be preempted only in process context. And of course, non-preemptive is the one which cannot be preempted. When speaking about process scheduling, processes are traditionally classified into three main classes: interactive, batch, and real-time. And these three types can be further divided into two types, that is the IO bound and the processor bound processes. And these two, of course, classification are not mutually exclusive, as processes can exhibit both behaviors simultaneously. For example, a word processor doing spell checking or macro calculation is an example of an IO bound processor using CPU to a great extent. Well, all the process scheduling algorithms try to maximize CPU utilization, throughput, and fairness, and tries to minimize waiting, turnaround, and response time. Well, this slide shows a brief comparison of some standard scheduling algorithms that most of us might have seen in the operating system concept course. Over here, the select function that basically describes how a process is selected. The W over here is the time a process has spent waiting in the run queue. E is the time a process has executed so far, and S is the service time, normally known as the burst time of a process. Well, over here, first come first served, SJF, and highest response ratio next are the non-preemptive algorithms, while the remaining are preemptive. The scheduling algorithms used by all modern operating systems are a combination of these standard algorithms. Okay, let us first have a quick recap of the traditional Unix System 5 Release 3 process scheduler. And this slide describes the major aspects of the scheduler, which employs 32 run queues from 0 to 31, as shown over here. And all these queues implement round-robin algorithm with a fixed time quantum of 100 milliseconds. There are a total of 128 priority levels, 0 to 49 for the kernel, and the rest are for the user level programs. Excuse me. 4 priority values are mapped on each queue. So 0 to 3 are mapped on run queue 0, 4 to 7 are mapped on run queue 1, and so on. Remember, in Unix, a lower priority number represents higher priority. So a process with priority 0 as the highest priority, and a process with priority value 127 has the least priority. A process enters in some queue, some appropriate queue based on its priority value, which is computed by this formula shown over here. And this formula is recomputed every second. So after every second, for every process, the priority value of that process is calculated using this formula, and it moves from one queue to the other. Maybe after some time, a process in Q2 moves to Q0, and maybe a process in Q2 moves to Q4 or 5 or 7 maybe. Well, the formula contains 3 values. It is sum of the 3 values. First is the base value, which differentiate between the user and the kernel priority. For user level programs, its value range from 50 to 127. The other second value, which is added up to the base value, is the CPU utilization of a process through interval I. It is actually calculated by multiplying the previous CPU utilization with the decay rate. And this decay rate in Unix System 5 Release 3 is 1 over 2. The third value which is added up is the nice value, which is a user controllable adjustment factor whose value range from -20 to +19 as shown over here, with a default value of 0. Well, this value is called nice because a process increases its nice value and in turn reduces its priority and show nice behavior to other processes by giving them the opportunity to run. In Unix, whenever a process is forked, it inherits the nice value of its parent. And we can always change this nice value by the nice or renice command or by the set priority system call. Well, this slide shows the 2 limitations of this scheduler. The first is, with very large number of processes, the overhead of recomputing process priorities is very high, and that has to be done every second. And since the kernel is non-preemptive, so high priority processes may have to wait for low priority processes executing in the kernel mode. Let's move on to the famous Linux Big O1 scheduler, designed by Ingo Molinar. And it was the process scheduler that was used by Linux kernel from version 2.6 to 2.6.22. Well, this slide shows the data structure used by Big O1 scheduler. Excuse me. Well, as the name implies, Big O1 scheduler can select the next process to run within a constant amount of time, regardless of the number of processes in the run queue. Every CPU has an associated run queue having 2 priority arrays, the active array and the expired array. And each of these arrays has 140 queues implemented as a linked list serviced in FIFO order. 0 to 99, these values are for real-time tasks, and 100 to 139 for the user task. The queues inside the active array over here contains the processes whose time quantum have not yet expired and are being executed by the CPU one after another. Once a process has consumed its time quantum completely, it is moved from this active array to the expired array. And once this entire active array gets empty, the two arrays are swapped, rather renamed. Other than these two arrays, a run queue also has two bitmaps of 140 bits each. And this bitmap is used to determine the highest priority non-empty linked list in the active array. For example, over here in this slide, you can see queue number 5, 7, 45 and 139 are non-empty. And the same we are seeing over here. The bits corresponding to these priority values contains 1. So the time to search the first on bit in this bitmap is constant. The time to access that linked list is again constant. And finally, selecting the process at the head of this list is again constant. So the overall time to select the process to run is constant. Now the question is, how a new process is assigned a priority level and time quantum in the very beginning when it is forked by its parent? Well, dear students, when a new process is forked, it inherits the static priority of its parent from 100 to 139 with the default static priority of 120, which is mapped onto the nice value of 0. And the time quantum a new process gets is almost half of the remaining time quantum of its parent. And when a process terminates, its remaining time slice is added to the parent's time slice. Well, over here, when the time quantum of an executing process in the active array expires, its dynamic priority is calculated as a function of its static priority and its interactivity. And based on this dynamic priority, its next time quantum is also computed, and it is moved to an appropriate queue in the expired array. For example, consider a process in queue number 7 in active array. After this process has consumed its time slice, its new DPI, that is dynamic priority, is calculated and it is moved to that queue in the active array. Suppose its dynamic priority is raised and it becomes 1, so from here it moves to this queue 1. And if its dynamic priority is lowered, so it moves to maybe queue number maybe 12 or 13 or maybe 14 in the expired array. And once both the arrays are swapped, the processes in the expired array are given their new time quantum and they start executing. Now let us see how the dynamic priority of a process is calculated. Well, this slide shows the formula which is shown over here. The dynamic priority is calculated using this formula. A process which spends much of its time waiting for I/O gets large value of bonus from 0 to 10. You can see if a process has slept for let's suppose 100 to 200 milliseconds, it gets a bonus value of 1, and if it sleeps for a time period between 300 to 400, it gets a bonus value of 3. So a value less than 5 means penalty and a value greater than 5 means bonus. For example, if a process has a static priority of let's suppose 120 and gets a bonus of 10, so the new dynamic priority will be 115 as per this formula. To compute its value, Linux famous task struct has a member sleep average, which is initialized with a value of 10 for every new process. For every time tick a process runs, this variable sleep average is decremented. And when a process becomes runnable after sleeping, it is incremented by how long it slept. I hope the concept of dynamic priority is clear to you all. And the next question is, how the Linux scheduler, big O of 1 scheduler, determine the interactivity of a process. Over here. Well, Linux scheduler uses a heuristic, and it says a process is considered interactive if it satisfies this condition. Bonus minus 5 is greater than or equal to static priority divided by 4 minus 28. So a process with static priority of 100, that is nice value minus 20, is considered interactive when its bonus exceeds plus 2 or average sleep time exceeds 200 milliseconds. And if a task is sufficiently interactive, for example, suppose a text editor, when its time slice in the active queue expires, it is not moved to the expired array, rather inserted back in the active array. Now let's see how the time quantum of our process is calculated. We know the first time the time quantum is half of the remaining time slice of the parent, but what about the next time? Well, next time every process gets its time quantum based on its static priority and interactivity in the range of 10 millisecond to 200 millisecond as shown in this table. For example, this table shows that if the nice value of a process is low and interactivity of that process is high, then its time quantum is quite large, that is 200 millisecond. And if the nice value is suppose high and the interactivity is low, then the time quantum is 10 millisecond. Finally, big O1 scheduler also supports CPU affinity. When a process is rescheduled to run on a multiprocessor system, it doesn't necessarily run on the same CPU on which it last executed, because the CPU may already be busy. If a process moves from one CPU to the other, the cache of the first CPU must be invalidated and the cache of the second CPU must be populated with the task data. And to achieve performance gains in cache optimization, the concept of CPU affinity is introduced. The big O of 1 scheduler tries to ensure this soft CPU affinity. That is, it tries to run the task on the same CPU on which it ran previously. And we can ensure a hard CPU affinity using a per process attribute that is known as CPUS allowed. And this is a 32-bit mask having 1 bit per CPU or core in the system. When a process is initially created, it inherits the affinity mask of its parent. Later, a process can always change it using the Schedtool command or maybe the Sched set affinity system call from within a C program. I think big O of 1 scheduler, the working of big O of 1 scheduler is quite clear. Let's talk about its limitation. And the first is it uses complex heuristic to determine if a process is IO bound or CPU bound to benefit one over the other. And secondly, a lot of code is there to manage the priority queues, at least 140 per processor. Okay, so now we are done with big O of 1. Let us talk about the completely fair share scheduler, CFS, which is implemented in Linux kernel from version 2.6.23 to the latest kernel, and that is 4.17, I think. It is also designed by Ingo Molinar and is based on rotating staircase deadline scheduler by Kon Kolivas. Well, in today's Linux kernel, there are 5 scheduling classes: stop, deadline, real-time, CFS, and idle. The scheduler iterates over each class in priority order, starting with the highest priority class. If a class has a runnable process, it is run. If not, then the turn of a process from the lower priority class comes. And in the very end comes a turn of the idle scheduling class, which runs last, never fails. It always returns the idle task. Let me talk about each class one by one briefly. Let's talk about the stop class first. This is the highest priority class. A process of this class can preempt everything and is preempted by nothing. This is used by task migration, ftrace, and maybe clock events. The second is a deadline class. This class is introduced in Linux kernel version 3.14. The scheduling policy used in this class is Scheddeadline and is used for periodic real-time tasks. The third class is the real-time class and is used for the POSIX real-time tasks like IRQ threads with priority values in the range of 0 to 99. Well, the scheduling policies used for this class are Sched and Sched. The fourth is the CFS class, completely fair share class. And this is the class under which most of the user processes, including the famous bash command interpreter, runs. It uses priority values in the range of 100 to 139. Remember, 0 to 99 are used over here and 100 to 139 are used by this class. And these 100 to 139 priority values are mapped onto the nice values of minus 20 to plus 19. The scheduling policies used by CFS are Sched normal, which is the default for all user processes, Sched batch for CPU intensive tasks, Sched ISO, which is unused or reserved, and Sched idle prio for low priority tasks. And finally, we have the idle class, which is the lowest priority scheduling class having no scheduling policy. The kernel idle thread runs when nothing else is runnable on a CPU. And a process in this class may take the CPU to a low power state as well. Excuse me. Now let us talk a bit detail of the CFS scheduling class. Before seeing how the CFS scheduler actually works, let us review some of the important data structures used by CFS. Unlike big O(1) scheduler, CFS scheduler implementation is not based on run queues. It actually maintains a time-ordered red-black tree to manage the list of runnable processes. Every process task struct, as shown over here, has a member struct Sched entity. And the Sched entity structure further contains the structure RB node over here to represent every node of the tree. And the Sched entity structure also contains a 64-bit field V runtime, which indicates the amount of time a process has run and serves as an index for the red-black tree. It is a V runtime which is shown over here inside the nodes in this diagram. Well, the task with the gravest need of the CPU, that is the lowest V runtime, are stored towards the left side of the tree, and the task or processes with the least need of the CPU, that is the highest V runtime, are stored towards the right side of the tree. Let us talk about the context switch and the time slice concept in CFS class. Well, dear students, in CFS there is no concept of time slice. Once a process is selected to run, during its execution, its V runtime is incremented. A context switch or rescheduling occurs when the V runtime of another task is smaller than the currently running task, or when a process that has higher priority than the currently running process is awakened. So what is the V runtime of a new process? Well, dear students, CFS keeps track of the minimum V runtime value among all processes in the tree. Whenever a new task is created, this value is given to it so as to give it a chance to schedule quickly and to achieve a good response time. The next question that might come to your mind is, what about priorities within a class? Well, dear students, CFS does not use priorities directly, but uses them as a decay factor of the V runtime. Let me repeat it again. CFS does not use priorities directly, rather use them as a decay factor of V runtime. So lower priority tasks have higher factors of decay, that is their V runtime grows faster, and higher priority tasks have smaller factors of decay, that is their V runtime grows slower. Finally, let's see how CFS handles CPU bound and IO bound processes. Well, of course, we know that we go of one use complex heuristic. Let us consider an example of text editor and a video encoder in CFS scheduling class. A text editor, as we know, is an IO bound process, and a video encoder is a CPU bound process. The video encoder executes most of the time and therefore will have high V runtime. On the contrary, the text editor sleeps for most of the time and therefore will have a very low V runtime. Hence, whenever the text editor wakes up, it preempts the video encoder, handles the user keys, and sleeps again. So that is how the CPU bound and IO bound processes are managed by the CFS scheduler. Okay, now enough of theory. Let us move on to the Linux terminal and practically see these concepts. Okay, so let me check out the attributes of my shell. ps-l long listing -q means I want to see the attributes of the process with the ID given in front, and $, as we all know, shows you the PID of the current shell. So these are the attributes of the bash process which is running right now, and we are mainly interested in this priority and the nice value. Remember, high value of priority means low priority, and over here we know that nice value is the adjustment factor that user can change to lower or to raise the priority of a running process. Let me say right now the nice value of this process is 0. Let me say I want to renice. Renice is a command that is used to renice the nice value of a running process. And let me say I want to make it 7, and I have to give the PID. And let me check again now. You can see the nice value has become 7. This process is behaving nicely now to other processes by raising its priority value and by reducing its priority. Remember, over here its priority value was 80 and over here it is 87. So that means its priority is lowered. Let me try to renice it to -20, and for that of course I need to be sudo renice to a value of -20 $. Let's check out. You see now the nice value is -20 and its priority value is 60, which is raised. Now this is a very high priority process because its nice value is in somewhere in the negative value. Okay, let us run a command. Let's suppose watch WATCH in the background. Watch is a command that is used to run another command every 2 seconds, and I'm running it in the background. And the value and the PID of this process is 6677. And let me check out the attributes of this watch program 6677. Remember, dear students, this was the shell having the nice value of -20. Watch is the child of the shell. So this nice value is inherited by the child program. So the nice value of the watch program, that is the child program of the shell, is also -20. Let me make the nice value of the shell back to 0. Renice $0. Let's check out. Well, fine. Let me kill the watch process as well. What is the ID of this? 6677. Okay. Let me use kill -9 6677, which is the PID of this, and I think now the watch program is no more there. Okay, so now we know how to change the nice value of a running process. Let us see how to run a program with a specific nice value. Okay, clear screen, and let me see ps -l -q $. So the nice value of the bash is 0, and let me run a command with a value of nice value of 7. Nice renice is a command that is used to change the nice value of a running process, while nice is a command that is used to run a program with a new nice value. And over here this -7 means 7, and if I want to say that I want to run a program with the nice value of -7, I need to put 2 hyphens over here. And let's say sleep 1000, and let me run it in the background so that I can check the values later. ps-l -q 6687. And you see the parent has the nice value of 0, and I have run the sleep command with a nice value of 7. Let me kill this 6687. Let me clear screen. Okay, so far so good. Now let us see what is Schedtool and what it can do for us. Let me say, if it is not installed on your system, you can do sudo apt-get install Schedtool. So it is the latest version. Fine. Let me do man Schedtool. Okay. So do read this man page. It is basically an interface to the Linux kernel scheduler and is used to query and change all CPU scheduling parameters of a process. Let me quit and say Schedtool and $, PID of the shell. Okay, so this gives you the PID of the process, the priority value, which is 0, and we know that this shell is running in the CFS scheduling policy, and the CFS scheduling policy runs under priority of 0. And the policy is n by n, I mean it is sched normal, and the nice value is 0, and over here the affinity is 7. That means 1 1 1 in binary. That means this process can run on CPU 0, CPU 1, and CPU 2. Let's see some details. Schedtool, let me give it an option -r, and you can see the scheduling classes. Well, as far as the real-time class is concerned, the scheduling policy is sched-FIFO and sched-RR. And remember, these two have the priority values from 1 to 99 as shown over here. And if I talk about the CFS scheduling class, the scheduling policies within the CFS scheduling class are sched normal, which is a default, sched batch for CPU intensive tasks, sched ISO, and sched idle prior. Remember, for this batch, this is used for the CPU intensive tasks that use long time slice but can be interrupted by other processes. And this sched idle prior, this is for low priority tasks. Let me talk about this sched FIFO and sched RR as well. These two are scheduling policies for the real-time class. If I talk about sched FIFO, processes are not preempted by others. However, they can leave the CPU via the sched yield system call. So you should be watchful when you are running a process under sched FIFO. Some of the other processes might not run in that case. As far as sched RR is concerned, it uses much small time slice than as compared to sched normal, and it of course have higher priority. Okay, now let me run another program on this terminal and let me run watch again. Remember, free is used to display the amount of free and used memory in the system. And this watch is going to execute this program periodically after every 2 seconds. Let me fall back and let me do ps-a, and you see this is the PID of the watch program 6723. Let me use Schedtool and 6723. So these are the attributes of this watch program. The same attributes which the shell is having, of course. Let us change the scheduling policy to sched patch. And for that, I need to run the command schedtool and I put a -b over here. -b means batch. If you want to do the sched RR, you can put an R over here. For sched FIFO, you can put an F over here. And then I need to give the ID 6723. Press enter, see this again, and you can see the scheduling policy has been changed to sched patch. Let's change the nice value as well. Schedtool, and to change the nice value, the option uses -n. And then I have to give the nice value, suppose 7. Then I have to give the PID, that is 6723. Let's check out. And you see the nice value has been changed from 0 to 7 now. Let's change the CPU affinity as well. And for CPU affinity, the option is -a. And after -a, I need to give a hex value. Let's go 0x2. I want to ensure that this process must run on CPU 01. 0x2 means there is a, let me write it down over there, 010, yes, something like this. So this bit is 0, this bit is 1, and this bit is again 0. So that means CPU 2. We will see the man page for this as well. Anyway, and then I have to give the PID, that is 6723. And if I run it again, you see the affinity has been changed. Let me show you the man page of Schedtool. It is a very descriptive page. Please do see the page if you come across something which I have not touched upon. It has talked about CPU affinity in detail, the affinity mask. So this over here shows that if you write down something like this, it will run only on CPU 0, and this means only run on CPU 1, and 7 means run on CPU 0, 1 and 2, but not on others, of course. Okay, let's fall back onto the slides again, and let's see what else we need to do. Okay, so up till now what all we have done is we have used commands on terminal to change the scheduling parameters of process. Let us see how we can do the same from within a C program. Well, this slide shows some system calls related to process scheduling. And the first is the nice system call. A process can use this system call to change its own nice value. And this get priority and set priority are the newer call. They are used by a process to get and set its own nice value or that of another process as well. And this sched get priority min and sched get priority max, these two calls are used to get the minimum and maximum priority range of a policy which is passed as an argument to these system calls. Then we have sched get scheduler and set scheduler. These two calls are used to get and set the scheduling policy of a process. And then we have sched get parameter and sched set parameter. They are used to get and set the scheduling parameters. Sched yield, as I have already said before, this system call causes the calling thread to relinquish the CPU and the process is moved to the end of the queue. Sched RR get interval. This can be used to get the time slice of the calling process running under sched RR policy only. Sched get CPU. Well, this is used to determine the CPU on which the calling process or thread is running. And finally, get affinity and set affinity. These two calls are used to get and set the CPU affinity mask of a process. So whatever you do on the shell using commands, you can implement that using these system calls from within a C program. Do read the main pages of all these for details, and let us move on to the Linux terminal to see some sample codes that use these system calls. Let me clear screen. Let me do cd to spvl, and I think it is session 21. Yes, we have certain programs over here. Let me vim sched1.c. Okay, so this is using the nice call, and over here I am just getting the original nice value because I'm passing 0 to it, plus 0, so no change. And over here I'm incrementing nice value by 7, and I'm doing a nice value to -2, and of course we know that only root can do this. I have done the error handling as well, and remember that nice may legitimately return a value of -1 on success. So we need to test for errors by setting error number to 0, as I have done over here before making the call to nice. And then I'm checking for a -1 return status and a non-zero error number after the call. So if this happens, that means nice has failed. Okay, so let me gcc sched1.c. let me get it as well, so that once I run it you can see it. Okay, you see the original nice value was 0, incremented the nice value to 7, and nice -2 has failed. And let me run it as sudo, and as sudo it has successful. So it has reduced the nice value with a value of -2 from 7, it has reduced to 5. And if I do something like this, let's go sudo nice -n -9 ./a.out. By this I mean I want to run this process with a nice value of -9, and of course you will get a -9 in the output over here now. Yes, -9, and after +7 it becomes -2, and after -2 it becomes -4. So that is great. Well, the limitation of this nice call is that it affects only the process that invokes it. Let me show you the man page of the nice call from chapter 2. So it only changed the nice value for the calling thread. So the better to use a set priority or the get priority call. Let me show you the man page of get priority. So this is the man page of get priority. Let me move on to the terminal, and if I have a page for this, yes, get priority and set priority. So remember, we have two arguments over here in the get priority, which and who. And this which and who basically identifies the process whose priority is to be retrieved or modified. The which argument actually determines how the who part will be interpreted. Over here inside the which part, we can have three values. One is prior process, the other is prior group, and the other is prior user. If I write a prior process, that means operates on the process whose PID is given over here in the second argument. If who is 0 over here, that means use the caller's PID. If I write down a prior group over here as the first argument, that means operate on all the members of the process group whose PGID equals who. And if who is 0, if I write down 0 over here, then the caller's process group will be used. And similarly, prior user operate on all processes whose real user ID equals who. Let me show you the code so that you can understand it properly. Let me do vim sched2.c. Okay, so what I'm doing over here is over here I'm using a get priority and getting the priority of this process, that is nice value of this calling process. over here I'm getting the nice value of another process, that is the parent process. Over here I have mentioned get ppid, and over here I have given 0, that is the calling process. Well, okay, so if I write down prior group over here and a 0 over here, that means I want to get the maximum possible nice value of the process group of the calling process. And over here I'm using prior user, that means I want to get the maximum possible nice value of the user group of the calling process. And finally over here I'm trying to change the nice value using the set priority, and I'm changing the priority of the current process to -2, and of course root can only do this, and after I'm getting it and printing it on screen. I hope the code is clear. Let me compile and run it. Okay, so you see the nice value of the calling process is 0, parent is also having a nice value of 0, maximum nice value of the calling process group is 0, and for the user group it is -11, and for changing the priority to -2 it has failed. Let me be root and run it as root. So now you see these values are 0, maximum nice value is -20, so root can change the nice value for the user group to -20 maximum. And this is also a success. The nice value of the process is changed. So that is great. So it is always better to use get priority and set priority instead of nice. Let me see another program, Schedtool3.c. Okay, so this basically is using the sched get priority min and sched get priority max functions, and for this policy it is going to get the minimum value and the maximum value, and we know they are from 1 to 99, I think, if I'm not wrong, and for sched others it is 0. Let's check out. Let me clear screen. Let me cat sched3.c. and you see that for sched RR it is 1 to 99, for sched FIFO again it is 1 to 99, and for sched others it is 0. And the same output we have seen for using the Schedtool as well. These are the same values. Let's see the other program, Schedtool4.c, and see what it is doing. This example queries the scheduling policy of this process and its time slice. Sched get scheduler is going to get the policy, and sched RR get interval is going to get the time slice. Let me just run it. You can see the man page for details. Okay, so you see the scheduling policy of the current process is 0, and that is of course sched normal, and this is the time quantum for that. Let me fall back to the slides. Please do go to the man pages of these calls and try running simple programs as a proof of concept. And this is sched yield as well, and I've already discussed this is also an important call. If a process wants to relinquish the CPU, it can use sched yield call. Okay, so dear students, I think that is enough for CPU scheduling. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. See you next time. Wish you all the best. Happy learning and Allah Hafiz.